let's move on now from conservation of mass to conservation of momentum. Where are we now? So fluid momentum is very important fluids, probably more relevant in a lot of cases than hydrostatics, because a lot of times fluid is not perfectly still, it is some kind of motion. And the design of many hydraulic structures, just floodgates, flow diversion blades, pumps, turbines, especially any devices that are harnessing or using fluids to harness or produce energy, depends on the forces that the fluid flow exerts on them. So in this section, we'll obtain the forces by using the linear momentum analysis, which is based on Newton's second law, which is written here. So the sum of the forces acting on a system is equal to mass times the acceleration of the system. And we can write the acceleration as the total time derivative, or that second term we can write as the total time derivative of the mass times the velocity of the system. So V is the velocity of the mass center, or the center of gravity of a system of particles composing the fluid. And our linear momentum, which we talked about earlier, which is capital P, is mass times the velocity, is an extrinsic property. So if we look at Reynolds transport theorem, again, for a fluid, and use a control volume approach, this works best for many momentum and force analysis type problems in fluids. So the rate of change of our extensive property. So here we have B, that's written right below. Our extensive property B is equal to our linear momentum, which is m times v. So we substitute that in here. And then our intrinsic property is just our mass times velocity divided by mass. So we just have velocity. So we have the same equation now as our continuity equation, except we're adding a velocity term in here and in here. So if this left-hand side of the equation is equal to the sum of the forces acting on the system, then we can substitute this into Newton's second law of motion, and we get the linear momentum equation. So this, on the left-hand side, is the sum of the forces acting on the fluid. Is equal to the local momentum change within the control volume and the convective momentum change. So the momentum change due to a change in position, and that position is either entering or exiting some control surface. So here the velocity term appears 3 times. 1, 2, 3. So the first term, the velocity of the fluid system at points within the control volume. So this could be the velocity with respect to our space within the control volume. 2 would be the velocity of the fluid passing through the open control surfaces. And then 3 represents the mass flow through the open control surfaces, which is a scalar quantity, rho times v dot dA. So let's look at some sort of example here to try and make sense of this. So if our flow is steady, we talked about steady flow, it means we have no local change of the momentum within the control volume. So that means at any point within our control volume, the rate of change with respect to time is 0. And because that first term has this time derivative outside, right here, if any of those terms inside our control volume are not changing with respect to time, so our velocity within our control volume at any fixed point is not changing with respect to time, and our volume is not changing with respect to time, then our first term, our local momentum change, is just equal to 0. So all we're left with is our last term, which is the integral over the control surface of the velocity of the fluid times density times the velocity of the fluid with respect to the control surface times dA. So we'll deal with why one of them is with respect to the control surface and one of them is not in a moment. We can further simplify this if we have steady and ideal flow. So if the density is constant, then we can integrate this over the area, and it's just equal to the sum of the velocity. This shouldn't be dA, this should just be the area. So if the flow is steady and ideal, rho is constant, and viscous friction is 0 because it's ideal, so it's inviscid. And we have sum of the forces is equal to the sum of the velocities times density times the velocity with respect to the control surface, dot product with the area of the control surface. So if we were to look at this example here, what would be our sum of the forces in the x direction, for example? Let's choose this direction as positive. So if we have this example here, it would be the sum of the forces of the velocity times rho times velocity dot product with our area. So we have 2 points. Our first term, so we should have 2 terms, one for the inlet and one for the outlet. So we have V in x times minus rho V in A in. The dot product of V in and A in would be negative. So we have a negative sign there. Plus the other end, the outlet, we have V out, the x component of the velocity going out times rho times V out times A out. The dot product would be positive. So this first term here is the components of the velocity in a given direction. So this would give us the information for the sum of the forces with respect to our fluid flow. So the right-hand side of the equation will be solved, and we need to look at the left-hand side. And usually what we'll be solving for is some sort of reaction force. Maybe we need to design the support for this system to withstand the forces that this section of pipe would be experiencing. So we would draw our free body diagram. So when the momentum equation is applied, there will generally be 4 types of external forces that can act on a fluid system contained within the control volume. So there would be pressure at the inlets and outlets from the fluid. There would be the weight of the fluid. There would be a normal force and a shear force. So they're counting pressure as the same force here, pressure in and pressure out. There might be different values, but pressure is one force, weight is another force, a normal reaction force, and a shear force along section of pipe. So for analysis, it's generally practiced to represent the resultant shear and normal forces acting on the closed control surface by a single resultant force. So we wouldn't show this as a distributed load all along. We would show this as just one single resultant force that would represent the total normal force and the total shear force acting on the control volume. So if we were to look at the opposite of these forces, so the opposite of the resultant force would be the effect of the fluid system on the surface. So this would be the force of the fluid acting on the control surface, which in this case would be that section of pipe. So the equations as we have them would be the forces of the pipe acting on the fluid, and the opposite of that would be the force of the fluid acting on the pipe. And the force of the fluid acting on the pipe would be called the dynamic force. So they're equal and opposite to the resultant force. So one last thing before we get into some examples, some specific cases, is introducing something called the momentum flux correction factor. So when we talked about our velocities, it's convenient to represent the velocity in terms of the average velocity, we call V bar, and the mass flow rate m dot across some area. So we can use a momentum flux correction factor so that we can use our average velocities if we know some velocity variation over the inlet. We can calculate that flux correction factor if we know the velocity profile and information about the geometry of the inlet or outlet. So if the velocity is constant over some area, then the correction factor is just equal to 1. And if the velocity is not constant over some area, then the correction factor is greater than 1. So essentially, all we'd have to do for these terms is include a beta dimensionless value, just as this equation right here. So when we're finding when we did our conservation of mass, we had our mass flow rates in minus our mass flow rates out was equal to the integral. Well, now we have our mass flow rates times our velocity in and our mass flow rates times our velocity out. But if we know this beta value and it's not equal to 1, then we can multiply by the momentum flux correction factor. And yes, it's annoying that it is the same variable that is used for our intensive properties, but that is convention, and I'll try to make a distinction when I'm talking about the momentum flux correction factor versus an intensive property. Typically, when we're dealing with the equations in this form, we're no longer talking about our intensive property because we've already substituted in depending on what law of motion we're looking at. So let's look at the force acting on nozzle. The end of a pipe is capped with a reducer as shown. If the water pressure within the pipe at A is 200 kPa, determine the shear force that glue along the sides of the pipe exerts on the reducer to hold it in place. So if this is water, and we're going to do our momentum analysis on this, we can assume it's ideal. We can use the density of water. No other information is given to us. We'll just say it's 1,000 kilograms per meters cubed. So our control volume is drawn in the question, and it is the region that contains the entire nozzle cap. And the reason that we want to contain this extra portion right here is so that we can, when we draw our free body diagram, we can consider the reaction forces due to the glue of the cap acting on that nozzle. So let's draw our free body diagram. Our free body diagram will just be of our control volume. So we have our nozzle. We have point B up top. We have A down below. So then let's draw some forces acting on our control volume. What are the forces acting on this control volume? Yeah, so we have the glue. So if we draw a single resultant force on each side for that, let's just draw this in blue so we can see it. We have our resultant force. And let's show this side divided by 2, because if we show 2 forces for that, then the sum of those will just equal the total resultant force. What other forces do we have? What about the pressure forces of the fluid? Do we have pressure at point A? Yes. So let's draw that in green. This would be a distributed load. And it is equal to pressure at A, which we know is given in the question as 200 kPa. That's the pressure inside the pipe. What about the pressure at B? Yeah, we don't really have any information, but from the picture, it looks like at point B, it's exposed to the atmosphere. So this can just be open. So PB equals P atmosphere. And if we're looking at gauge pressures, then that is just 0. So we're assuming that 200 kPa is gauge pressure. So this is our free body diagram. So we have an equation for all of the forces, or so we have, sorry, an expression for all of the forces acting on our control volume. Now let's use our continuity equation to figure out what are the forces acting on our control volume just due to the fluid flow. So if we write continuity, we need continuity to determine the volume flow rate out of the pipe. So this is steady flow. So continuity, remember, is our conservation of mass. So we have steady flow. So the rate of change of mass in our control volume is 0. So all we're left with is the mass flow rates in and the mass flow rates out. So we have 0 minus rho A VA area at A plus rho B VB area B. Is equal to 0. We don't need to know the density for this because both sides are just equal to 0. So we can just divide both terms by the density. Density is ideal, so it's constant. Rho A is equal to rho B. So then if we rearrange this, we have negative VA times the area at A. So we have our diameter is 100 millimeters. So we have pi times 0.05 squared plus VB times pi times 0.0125 squared. is equal to 0, we'd end up with VB is equal to 16 VA. So we know the velocity exiting the nozzle is going to be 16 times the velocity of the fluid entering the nozzle. So let's go back to our question. It says determine the shear force that the glue along the sides of the pipe exerts on the reducer to hold it in place. So we have information about the velocity of the fluid entering and exiting. We have the areas. We know the flow rate difference. We know the pressures at A and B. We have a free body diagram. Now let's write our momentum equation. So if we write our linear momentum equation, sum of the forces equal the derivative of the respective time, it's control volume times our velocity, rho dV, velocity rho times velocity fluid with respect to the control surface times dA. So how can we simplify this? How can we simplify this analysis? This force that's also a vector. So we said that the flow is steady, so there's no local change in momentum. So the first term is just 0. And all of the forces that we care about from a free body diagram are acting in the vertical direction. So let's just write this now in component form, some of the forces in the y direction, and we'll write everything in terms of the y direction. And we'll take our upwards direction to be positive. Some of the forces of the y direction are going to be 0. We have the fluid exiting at point B and entering at point A. So at point A, we're going to have mass entering the system. So that's going to be minus our velocity at A times times rho A VA area of A. So those velocities, we're assuming, are uniform, and they're already in the y direction, so all those components are already in the correct direction. So this is our inlet, plus the velocity at B, times rho B, VB times AB, which is our outlet. So if we simplify this, we have our sum of the forces in the y direction are equal to our density is just the density of water. So rho water, and all we're left with is VB squared times AB minus VA squared AB. So we have a second equation. So as it is right now, do we have enough information to solve? So let's review what we've done so far. We have a nozzle. It's filled with water, and we did our free body diagram of the pressure or the forces acting on the nozzle, which was our control volume. We used continuity to relate the velocities at the inlet and the outlet, assuming steady flow and conservation of mass. And then we use our linear momentum equation to find an equation for the sum of the forces, which would be equal to those reactions from our free body diagram. But we still don't know what the values of VA or VB are. We could substitute equation 1 into equation 2, and we can get an answer in terms of VA or VB, but we still don't know what VA or VB are, so we don't know what the reaction forces are. So what's another equation that you think we could use that could tell us what the velocities at point A and point B are? Yeah, great. We need to use Bernoulli. So let's now write Bernoulli. So if we writing it from point A to point B, we have pressure at A over gamma plus VA squared over 2G plus ZA is equal to the pressure at B over gamma plus VB squared over 2G plus ZB. So we don't have any information about the difference in elevation from A to B. So we can just neglect that difference as having an effect on our pressure. So we'll assume that our elevation ZA and ZB are relatively similar. So all we have left with are the other two terms. So the pressure at A we said was 200 kilopascals. And our specific weight is 1,000. Gamma is just rho times G, so 1,000 times 9.81 plus VA squared over 2G, so 2 times 9.81 is going to be equal to our pressure at B, which we said is 0, plus VB squared over 2 times 9.81. So if we simplify this, we would just get VB sorry, if we simplify this with equation 1, let's call this equation 3. Let's put equation 1 into equation 3. Equation 1 was from our conservation of mass. So VB is equal to 16 VA. We would find VA is equal to 1.252 meters per second. And then VB is equal to 20.04 meters per second. So if we put this equation now 4 into our linear momentum equation, we have rho W, so 1,000 times VB with 20.04 squared times AB pi times 0.0125 squared plus, rather minus, BA, which is 1.252 squared times pi 0.05 squared. So that is the right-hand side of our momentum equation. This is now equal to sum of our forces. We go back up to our free body diagram. We have 2 times FR over 2 going downwards. So just FR going downwards, and then PA times the area going upwards. So we have plus PA times AA minus FR. PA times AA is 200 times 10 to the 3 pascals times pi times 0.05 squared. So finally, we have an equation where we only have one unknown. We can solve for that reaction force, the glue, and that would be equal to 1,390 newtons. And that force would be acting downward. So that is the force pushing back on the fluid flow. So the dynamic force is the opposite of the resultant force. The dynamic force is the force that that cap would feel from the fluid. So the fluid is trying to push that cap off with a force of 1,300 newtons. Which is pretty significant. So when we get to these linear momentum problems, you now have quite a big toolbox of equations you can use to try and solve them, to solve all your unknowns. And this is a good example because it shows basically all the different kinds of equations that you would need to solve a problem. So we have our free body diagram, we have continuity, we have linear momentum, and then remember back, we have Bernoulli. We put that all together and we can solve the reaction force. So let's do another example. So in this example, we have a sluice gate located at G, and it's in the open position. Water flows out from under the gate at a depth of 1 meter. If the gate is 3 meters wide, determine the resultant horizontal force that must be applied by its supports to hold the gate in place. Assume the channel behind the gate maintains a constant depth of 5 meters. So basically, what is the force, reaction force Fg that's going to hold that gate in place? So let's start with our free body diagram. Our control volume is shown. So let's draw that. Our boot shape. We have the weight of our fluid acting downwards. We have the force of the sluice gate acting on the fluid. We have our normal force from the ground supporting that weight of the fluid. And then we have our distributed fluid loads, which we can write as a resultant force over here, and then likewise on this side, and we can draw our resultant force at A. So this is quite an involved free body diagram. And we have no information about the density of the water, but since it is water, we'll just assume the density is 1,000 kilograms per meter cubed. So our control volume is fixed, it's not moving. Because it says that the channel behind the gate, so at A, maintains a constant depth of 5 meters. And past the gate is a constant depth of 1 meter. We can assume that it's also steady flow. And we also are going to assume that the velocity right here, entering point A and exiting point B, are uniform. So that represents the average velocities. So let's think about what we need to do based on the problem that we just solved. We have to figure out the velocities at point A and the velocity at point B. So to do that, we would need to have two equations to solve. So if this was just a question from before, we're looking at just the dynamics of the problem, and we asked, find the velocity at point B, given this information, and the velocity at point A, we could solve for that by using our Bernoulli's equation and our conservation of mass. So once we have the two velocities, then we know everything that we need to solve our linear momentum problem. So let's start by using continuity and Bernoulli's equation. So our continuity equation ddt of the control volume of rho times dv plus the integral of the control surface, rho is a velocity is all equal to 0. It's steady. So our left term is 0, so all we have is our mass flow out plus, mass flow in. Which we can write as negative VA times the area at A, so 5 meters tall. And the width is 3 meters, so the gate is 3 meters wide. Plus the velocity at B. And it is 1 meter tall and also 3 meters wide. So from this, we get an equation VB is equal to 5 VA. Let's use Bernoulli next. Find another relationship between the velocities, which uses the pressures between the two and relates them that way. P1 over gamma plus V1 squared over 2G plus Z1 is equal to P2 over gamma plus B2 squared over 2G. I guess I should write this in terms of B. So we kind of have a hint given to us in this problem. We have 0.1 for a fluid element along the surface and 0.2. So if this is our streamline, pick a point on the surface at both points, then our pressure for both of those is the same. It's atmospheric pressure, so our pressure is just 0. We have a change in elevation of 4 meters, and we have our velocity at A and our velocity at B. So we can write the first terms are just 0. So we have VA squared over 2 times 9.81. Our Z coordinate at A is 5 meters. That's equal to 0 plus VB squared over 2 times 9.81. And our elevation at point B is 1 meter. So from this, we get an equation, VB squared minus VA squared is equal to 78.48. So let's put equation 1 into equation 2. VA is 1.808 meters per second. And VB is equal to 9.042 meters per second. So we have a free body diagram, continuity equation, Bernoulli equation, solve for the velocities at the inlets and outlets. Now let's apply our linear momentum equation. Sum of the forces is equal to partial derivative with respect to time of the integral of the controlled volume, our velocity times rho dV, plus the integral over the control surface, our velocity times rho, the velocity of fluid with respect to the control surface, dot product with our control surface. So if we look back at the free body diagram and we want to solve the forces Fg, we don't really need to consider the forces in the y direction. We can just choose the x direction. So we only care about the forces in x. So let's write this in component form, just the forces in the x direction. And we'll write this as positive. Sum of the forces in the x direction will equal, this term is steady, and this term just goes to 0. So we have steady flow. So 0 plus velocity at B flowing out times VB AB plus velocity A inlet minus VA AA. So we consider it this way, where we just keep track of the dot products, and that will take care of the signs for us if we choose. And this is equal to those forces. So from our free body diagram, we had minus Fg plus Fa minus Fb. So now we have to think back, okay, what is the resultant force A and B? This is going to be related to our forces on plane surfaces. So what is the resultant force A? Who knows our resultant force at A? Hydrostatic force. Static pressure at A times the area at A, yes. But the static pressure is changing with depth, so it's not constant. So if we look at this problem as if it's a mechanics problem and we have a distributed load, how would we calculate the equivalent force of a distributed load if it looked like this? And we knew information about the pressure would be equal to H times gamma. Yeah, so good. So we would have 1/2 times 1,000 times 9.81, which is the specific weight of the fluid, times the depth, 5 meters. That would be the resultant force. Sorry, the resultant total pressure times our area. We do the same thing for FB. 1/2 times 1,000, 9.81 times 1, times 1 times 5. So if we cared about the position, if we wanted to find moments, then we would need to know where the force at A is located. And yeah, that would be 1/3 of the distance from the bottom. But since we're just doing some of the forces in the x direction, we don't care where Fa is acting, we just care which direction. And it's acting in the horizontal direction. So these are the quantities for our forces. So we have finally Fg is equal to let's call this equation 3, 4, 5. So if we put all these together, we have Fg is equal to 156.9 times 10 to the 3 newtons, or 157 kilonewtons. So are there any questions about this example? No questions? All right. So let's look at linear momentum now if we have a moving body. So for some problems, or I would say many problems, a blade or a vane might be moving with a constant velocity. And when this occurs, the forces on the blade can be obtained by selecting a control volume of the same shape and size that moves with the body. So it's the exact same as we had applied with our conservation of mass equations, our continuity equation. So the velocity of the mass flow in the momentum equation are measured relative to the control surface. Then now that velocity term that we had before with no subscript is just equal to the velocity of the flow with respect to our control surface. So if we have steady flow, or if we have a control surface that's moving with our moving body, then we have a steady flow condition inside the control volume, and that first term will go to zero. So this term here will go to zero if we have steady. We saw earlier a case where it didn't have steady flow, and that was when we had a compressible gas filling up a tank. The amount of mass inside that tank was changing with respect to time. So that wasn't steady flow inside the tank, it was transient, it was being filled up. So if we have steady flow, it means that there is no relative change within the control volume. So let's look at a truck now. It's moving to the left, 5 meters per second into a 50 millimeter diameter stream of water, which has a discharge of 8 liters per second. Determine the dynamic force of the stream that the stream exerts on the truck if it is deflected off the windshield in the vertical plane. Let's start by drawing our free body diagram of our control volume. Our control volume is just this shape here. And we're just going to find our reactions flowing on this, or reactions acting on this control volume. So we're going to have some X component reaction and some Y component reaction. What about the force of the pressure that is entering and exiting? What's happening here? Any thoughts? Well, is there a force due to the pressure here? Yeah, if we're considering gauge pressure, and at these points it's just an open fluid flow, it's exposed to the atmosphere. So our pressures here are equal to zero, so there's no forces acting on our fluid control volume just due to the pressure. So the only forces we have are the reaction forces from the truck windshield deflecting that fluid column. And because it's water and we don't have any other information, let's just assume it's an ideal fluid, which means it's incompressible and inviscid. And we'll assume it's water with a density of 1,000 kilograms per meters cubed. So we have information about the truck. The truck is moving to the left at 5 meters per second. So what velocity is that? What velocity term is that? Is that the velocity of A, velocity of B, the velocity of the control surface? Is it the velocity of A with respect to the control surface? Right, that's the velocity of the control volume. So CV is fixed to the truck, so the control volume is going to be moving at the same speed as the truck, which is 5 meters per second to the left. So if we say, let's choose this as positive, then the velocity of the control surface is equal to minus 5 meters per second. So what is the velocity of the fluid at point A with respect to the control surface? So we know the velocity of the control surface. What's the absolute velocity of the fluid? In the question, we know Q is equal to 8 liters per second. And we know the diameter of the stream of water is 50 millimeters. So the velocity of our fluid, the absolute velocity of our fluid, we can find from our volume flow rate equation. Q is equal to VF times AF. So we can write this as 8 liters per second is 8 times 10 to the minus 3 meters cubed per second, divided by our area in meters squared. Our area is 50 millimeters. And then our control surface velocity is 5, so minus 5. The velocity of our fluid with respect to our control surface at A is equal to 9.074 meters per second. So if we think about that, that makes sense. If we're shooting fluid at the windshield and we're sitting in the car and we're driving towards that fluid stream, it would appear to be moving towards us faster than it would to someone standing on the side of the road. So if we drive towards it, its relative speed will increase. So if continuity must change or must be applicable, we can show that the average, or if we apply Bernoulli's equation, we can show that the relative average speed is maintained as the water flows off the windshield at B. So we're neglecting the elevation effect again. And because the size, the column we're saying isn't changing, that would just show us that the open area in B would be the control surface, must remain the same as A. So from continuity, we can say the velocity of the fluid with respect to A, or the control surface at A times the area at A, be equal to the velocity of the fluid with respect to the control surface at B times the area at B. So this equation is just saying if we were sitting on the truck and we were watching from the side that fluid column, so let's look back over here. We're sitting with respect to the truck. The fluid entering here, because the area isn't changing, would appear to be the same velocity as the fluid exiting the truck relative to that truck. If we were motionless, the truck wasn't moving at all, then that would be obviously true. We have conservation of mass, and Bernoulli's equations would show that the velocities at the inlet and outlet at A and B are the same if the truck isn't moving. The same thing is true as if the truck is moving, except now the velocities are not equal to the velocity of the stream, it's the velocity of the stream relative to the truck. So we can also assume that A is equal to A B. And that's an assumption based on the information given to us in the problem. So we have information about the velocity. We know we have a numerical value for the velocity. So we can just go straight into the linear momentum equation. Sum of the forces. Since it's steady, I'm just not going to write that first term. Just know it's 0 plus the integral of the control surface of V rho So if we rewrite this with the values that we just found, some of the forces are going to be equal to velocity of the fluid with respect to control surface at B times rho VFB times AB. And that's exiting at point B, so that's positive, plus the velocity of the fluid with respect to the control surface at A times negative, because this is entering, so it's a negative dot product, VF with respect to A, the area at A. So now what we can do is we can break this up into each component. Some of the forces in the x direction. We have VFB and the component of VFB in the x direction would be cosine 40. So VFB cosine 40 gives us the x component of our velocity of the fluid with respect to the exit at B, multiplied by rho VFB AB, plus the velocity of the fluid at A. It's already in the x direction, minus rho VF AAA. And this would be equal to minus our x direction force is in the negative direction. If this is what we have as positive, so it's equal to minus Fx. So we solve this, we know all those values. Force in the x direction, reaction force is 37.83 newtons. And we want to find the y component. Let's do the sum of the forces in the y direction. So now we have V FB times sine 40, which gives us a y component times rho FBAB. And our second term, we don't have any component of the velocity at point A that is in the y direction, it's just horizontal. So that's equal to 0. Our second are at our inlet, and this is equal to Fy, because we drew Fy in the positive y direction. So we have Fy is equal to 103.9 newtons. So our total force is equal to 111 newtons. It's weird writing 111, it looks like binary. So this is the force acting on fluid. The dynamic force acts in the opposite direction. So are we okay with this? I think the tricky part of this problem is determining the relative velocities. So for point A, it should be pretty simple because it's all in the horizontal direction, which is the motion of our control surface. So this we would just call our fluid with respect to control surface at A. And if we look at continuity, we know that we have steady state, so the flow rate in is going to equal the flow rate out of our control volume. And our areas at the entrance and exit we'll assume are equal. And if we're sitting on the hood of that truck and we're not looking at anything but the control volume, the velocity coming into the control volume would appear to be the same as the velocity going out. And those are our relative velocities. So the relative velocity at A is equal to the relative velocity at B. And since we know the relative velocity at A, we know the relative velocity at B, we can then solve our linear momentum equations. So let's look at some applications for linear momentum where we have some work being done, and this is due to a force of a moving fluid. So propellers and wind turbines are one useful application of harnessing energy of a moving fluid or providing energy to a moving fluid. And they both act in the same way, just kind of opposite to each other. So they both act as a screw, or like a screw, by using several blades mounted to a rotating shaft, and the linear momentum of the fluid is transferred into rotational energy in the propeller or turbine, or vice versa. So the wind powers a turbine, or a propeller powers the wind, or drives the wind. So in the case of a boat or airplane propeller, if we apply a torque, it causes linear momentum of the fluid in front of the propeller to increase as it flows towards, then through the blades. So if here is our system, this could be a propeller or a turbine, just depending on where power is being supplied. We look at this example here of a propeller where we're increasing the velocity of the fluid within the streamline, the control volume, after it passes through. We have a increased area at 0.1. The area decreases to 0.3, which is the same area swept by the blades. And between 0.3 and 0.4, we're assuming that the velocity is fairly constant. And that's quite true. It is more or less constant. So the fluid is accelerating from 0.1 to 0.3. From 0.3 to 0.4, the velocity is more or less constant. And then it accelerates again from 0.4 to 0.2 at the outlet. So we would consider the inlet of the control volume around a propeller or a turbine at 0.1, and the outlet would be 0.2, and 0.3 and 4 are right in front and right behind the blade. Figure B is showing the pressure variation that's going across that propeller. So what is driving this is the propeller is increasing pressure on one side and decreasing pressure on the other. And that change in pressure causes fluid acceleration. So the fluid velocity is going to increase. So it's all driven by that changing in pressure. So when we have a change in momentum of the fluid, there's going to be a reaction force. So the change in momentum creates this reaction force on the propeller, which then pushes it forward. So a wind turbine works the opposite way, where you're extracting fluid energy or you're developing a torque from the wind as it passes through the turbine blades. So during the operation, we can use the concept of our stream tube that we talked about when we were looking at fluid visualization. If we imagine this as a circular tube of our control volume, then if those are streamlines, then there's no fluid crossing the streamline. And the pressure on the outside control surfaces, because there's no fluid transferring the streamline, the pressure gradient is perpendicular to that. So the pressure along that is constant. The pressure along a streamline is constant. And we'll say it's equal to the atmospheric pressure or the surrounding pressure of the undisturbed fluid. So we'll say this is equal to our gauge pressure, or atmospheric pressure. So let's look at our linear momentum equation applied to repeller. So we have our momentum equation for our propeller. We can write this as the force acting on the fluid, the reaction force on the fluid. If we have a steady flow, this first term is just going to 0 because our flow is steady. We're not accumulating mass inside our control volume over time. We're not accumulating momentum either. So our first term is just 0. And what we're left with is our flow terms in and out of our control surface, or our momentum in and out of our control surface. Our momentum is our velocity times our mass flow rate. So we have V2 times m dot 2 minus V1 m dot 1, which we could just write as equal to V2 times rho V2A2 minus V1 rho V1A1 . So if we know our conservation of our continuity equation, continuity would say that essentially our flow rate we have steady, we're assuming incompressible flow. We would have Q is equal to V2A2, and it would be the same at the exit, or at the entrance, V1A1. And it would also be the same at the middle region between 3 and 4, where we'll assume we have some average velocity, V, and the area swept by our blade. So we're assuming our blade has a radius of R. So let's draw this here. Our blade would have a radius of R. So we can relate the velocities at each of these points with our continuity equation for a steady flow. So if we substitute this in, what we end up with is our force is equal to the density of the fluid times the velocity times pi r squared times V2 minus V1. So here just remember our velocity at point 3 and point 4 are equal to our velocity at V. So typically we don't really know our velocity at points at the propeller. We know the velocity of the wind all around. So we know what V1 is. So we want to try and write this equation in terms of V1 and the velocity V2, which would be the fluid that is being thrust outwards from the propeller. So we got to figure out how can we determine some equation for the velocity. So let's apply Bernoulli's equation. So if we use the Bernoulli equation, we would have P over gamma plus V squared over 2G plus Z is equal to some constant. And if we assume that there's no elevation change, we can just get rid of this term. And if we did this from point 1 to point 3, along a streamline for a particle from point 1 to point 3, Bernoulli's equation would just be V1 squared over 2G is equal to the pressure at point 3 over gamma plus V3 over 2G. And if we also did this from 4 to 2, we would have P4 over gamma plus V squared over 2G is equal to V2 squared over 2G. So because point 2 and point 1 are on the control surface, we said that's equal to the atmospheric pressure. So So gauge pressures there are just 0. So the pressures at 1 and the pressure at 2 are just 0. The only term we have left is the velocity term. So, and then lastly, we combine this with V3 is equal to V4 is equal to V. And if we rearrange and we solve, we can get the relationship P4 minus P3 is equal to 1/2 rho V2 squared minus V1 squared. So we've applied Bernoulli's equation, try and relate the velocities between point 1 and point 2. And we have a new equation. So finally, we can equate this with our equation above. So we had F is equal to rho, where is that equation? Rho V pi r squared V2 minus V1. So this is equation 2 and 1. We can relate the difference in pressures here to the difference in our forces. So the force would just be equal to the pressure at 4 times pi r squared minus the pressure at 3 pi r squared. Since the velocities aren't any different, the velocity at 3 is equal to the velocity at 4. So from 3 to 4. So if we do this and we substitute that into here, we end up with velocity v is equal to velocity at 1 plus the velocity at 2 divided by 2. So this seems like a lot of extra work just to prove that the velocity in the middle is equal to the average velocities. And it's actually so important that it's been developed into, it's called now Freud's theorem. So this indicates that the velocity of flow through the propeller is actually the average of the upstream and downstream. So if you have a velocity of the fluid entering the control volume that you know, and you have the velocity that's being thrust or the exhausted out of the control volume that you know, you can calculate the resultant force on that volume of fluid, and that's equal to this equation here. So all we've done here is substitute this result back into here. So if we have a propeller, and we know the velocity at 1, we know the velocity at 2, and we know the radius of the propeller, so we can calculate the area swept by the propeller, multiply that by the density, and that would give us the thrust force developed by that propeller. So whenever we're talking about forces and harnessing energy from a fluid, typically we're going to be talking about power and efficiency as well. So the power output of the propeller is caused by the rate of work done by the thrust. So we can write W dot, which is the rate of work, W, is equal to the force times the velocity at point 1. So if we can show that diagram again with this, the power output is equal to force times the velocity at 1. The power input is the rate at which work is needed to maintain the increase of velocity of the slipstream from V1 to V2. So our input would be Wi dot, which is the force times the velocity at the propeller. So finally, we have the ideal efficiency, which is our symbol for eta of a prop, is the ratio of the power output to the power input, which is 2 times V1 divided by V1 plus V2. So in general, we have some notes on efficiency of propellers. The propeller's actual efficiency will increase with the speed of the control volume, or the speed of the aircraft or boat that's attached to. Although it's never going to equal 100%, because as we increase our speed, we'll increase the losses due to friction, but there is some maximum. But in general, the efficiency is higher at a higher speed. The point where it begins to drop is when the tips of the blades start to exceed the speed of sound, or the pressure at the blade tips start to reach the vapor pressure of the fluid. So for example, when this occurs, the drag force, the propellers of a plane would significantly increase due to the compressibility of the air as we approach the speed of sound. And experimental tests on airplane propellers show that their actual efficiencies range between 60 and 80%. In the case of boats, where we have a liquid medium or a liquid fluid, then cavitation can occur, and that's when the pressure at the wingtips or the propeller tips is low enough that we start to have cavitation. We reach the vapor pressure of our fluid. So that is kind of limiting. If we have vapor pressure behind the fluid, our efficiency drops dramatically. So boats with a smaller diameter propeller tend to have a lower efficiency, and they're often between 40 and 60%. So let's do an example with a propeller. So we have a motor on a small boat, has a propeller with a radius of 60 millimeters. If the boat is traveling at 2 meters per second, determine the thrust on the boat and the ideal efficiency of the propeller if it discharges water through it at 0.04 meters cubed per second. So let's assume again we have 1,000 kilograms per meter cubed. The average velocity of the water flowing through the propeller is and the volume flow rate is just equal to velocity times the area. It's got a radius of 60 millimeters, so pi times 0.06 squared. And the discharge rate is 0.04 meters cubed per second. So from this, we can get our velocity of the fluid at the propeller is equal to 3.537 meters per second. So where can we go from here? It's asking, determine the thrust on the boat and the ideal efficiency. and the boat is traveling at 2 meters per second. Where should we go? What are equations we know that we can use for propellers? So for a propeller type problem, we've already done all of the linear momentum equation work, the Bernoulli equation work, the continuity equation work, and we have our set of equations that are tools that we can use. So we know one equation is the velocity at the prop is equal to the velocity into the prop plus the velocity out of the prop divided by 2. So it's the average of the velocities in and out. And we also know Freud's theorem, which is the thrust, is equal to rho times pi r squared over 2 v2 squared minus v1 squared. So we know v. How can we find v1 and v2? So we've already applied Bernoulli and our continuity equations for Q, and we got these two equations. So we have this value. Do we have any other of these ones? Do we know v1 or v2 from the problem? If the boat is traveling at 2 meters per second, then what is the speed of the fluid entering the control volume? Right. So v1 is 2 meters per second. So we can say v2 then we rearrange this as 2 times v minus v1. So 2 times 3.537 minus 2 is equal to 5.074 meters per second. So when we have a propeller, these are our two toolbox equations, and our velocity entering would be the same as our velocity of our moving CV, unless there's some flow of the fluid with respect to the boat that would be given a different way. But for a boat traveling with a propeller, the velocity of the boat, we're assuming that the velocity of the boat is given with respect to the water, and so that velocity would be the velocity into our control volume. So we can calculate v2 and v. So once we know v1 and v2, we use Freud's theorem. And we have F is equal to 1,000 times pi. The diameter is 0.06 squared over 2 times v2 squared minus v1 squared which is equal to 122.94 newtons. So now the second part of the question is, what is the efficiency of the propeller if it discharges water at 0.04 meters cubed per second? So we could calculate this two ways. We said that the efficiency is equal to the rate of work output divided by the rate of work input, which is equal to FV1 divided by FV. So if we did this, we would get 56.5%. The other way we could solve this is, say, using our other equation, 2 times V1 divided by V1 plus V2, 2 times 2 over 2 plus 5.074, and we would get the exact same answer. So both methods work. So that is a propeller. So we're past our time. We'll leave it here and we'll pick up on wind turbines on Thursday. And we'll finish up linear momentum and hopefully get started on conservation of energy.